All right, we've got 2 days of notes. Today we're going to do day 1 and day 2 notes. A quick review. Remember that an isotope are atoms of the same element, which means that they have the same atomic number or same number of protons, and they have different numbers of neutrons, which means that they'll have a different mass number. Remember, mass number is determined by protons plus neutrons. An example would be carbon-12 and carbon-13. Carbon-12 would have 6 protons, carbon-13 would have 6 protons, but carbon-12 would have 6 neutrons, carbon-13 would have 7 neutrons. The atomic number, again, is the number of protons in the nucleus. This cannot change during chemical reactions. The proton number always remains the same because an element isn't going to change from one element to another in a chemical reaction. The mass number, again, is the number of protons plus neutrons that's in the nucleus of an atom. A shorthand way of indicating the mass number and atomic number for an atom is you write the symbol for the element, and then you're going to use 12, which would be the weight, and 6, which is the atomic number. Radioactivity was first observed by Marie and Pierre Curie in the 1900s, and they were using uranium. Radioactivity is the process by which substances spontaneously emit rays and particles, which is what radiation is. Radioactivity differs from chemical reactions in a number of different ways. In a chemical reaction, atoms attain stable electron configurations by losing or sharing electrons. In a nuclear reaction, the nucleus of the unstable isotope gains stability by undergoing changes. So in chemical reactions, the only thing that's changing is electrons, either being lost or shared. And in nuclear reactions, what is being changed is the nucleus of the atom. Unlike chemical reactions, nuclear reactions are not affected by changes in temperature, pressure, or the presence of a catalyst to speed up a reaction. Nuclear reactions of an isotope cannot be sped up. They can't be slowed down or turned off. Once a nuclear reaction starts, it's going to go at the speed that it's going to go until it's completed. Unstable radioactive isotopes, otherwise known as radioisotopes, are transformed into stable, non-radioactive isotopes of a different element. Now, they're literally changing from one element to another, because you'll see that the proton number is going to change. Radioactive decay is the process by which unstable nuclei emit radiation and energy in order to obtain a more stable state. There are 3 different types of radiation: alpha radiation, beta radiation, and gamma radiation. Think Incredible Hulk when we're thinking gamma radiation. Let's look at each one individually. Alpha radiation, we're going to use the symbol, it looks to me like a lowercase a. This is really a helium nucleus that has been emitted from a radioactive source. It'll contain 2 protons, that's what makes it helium, and 2 neutrons. This will have a positive 2 charge because we only have protons, we don't have any electrons. It's going to have a positive 2 charge. Usually we're going to write it as, let me back up here. We're going to write it as He or the symbol. Now we're also going to put a 4 here and a 2 there. Let me speed through this. Remember when Rutherford, he used alpha particles to discover the nucleus of the atom in the gold foil experiment. He was actually shooting alpha particles. If an alpha particle hit the nucleus, it would bounce in different directions. There's the 4 and the 2 that you need to put in your notes. Okay, it's going to be written as He with a 4, meaning that it has a mass number of 4, and of course it has 2 protons. Due to its large mass and charge, alpha particles do not travel very far. They can't penetrate very well. A sheet of paper or the surface of your skin will stop them. However, if you ingest them, they are toxic. So if you eat something that has alpha radiation on it, that's not a good thing. An example of alpha radiation is the alpha decay of a uranium-238. Uranium is atomic number 92, and it has a weight of 238. It's an unstable element. When it undergoes radioactive decay, it's going to become thorium-90, and the weight of the thorium will be 234. What will be released is an alpha particle. So notice that we have not lost or gained anything in our reaction. The conservation of matter has been conserved. This has 92 protons on this side. We have 90 protons here plus 2 here, so we haven't lost any protons. This atom has actually been split, giving off a helium nucleus and changing the element to thorium. Notice also the weight has not changed. We had 238 atomic mass units over here. Thorium will have 234, and the helium particle that was given off has a mass units of 4. So we have 2 protons, 2 neutrons in this particle here. Let's talk about beta radiation. This results from breaking apart of a neutron into a proton and electron. Yep, that's right. Protons are literally a part of a neutron. Electrons are also parts of a neutron, which kind of makes sense because we know a neutron has an overall charge of nothing. It's neutral, and that would explain why if you break a neutron apart, we have a proton, which has a positive charge, and an electron, which has a negative charge, that'll be emitted. Now, usually we're going to write this as an E because we have an electron, or you can use a beta symbol. This has much less mass than an alpha particle, and therefore can penetrate more easily. It can pass through paper, but is going to be stopped by foil or wood. When you're writing the symbol using an E, we're going to say the mass is 0, and we're going to have a -1 charge. Or sorry, -1 proton number. Because we're literally losing a proton. So we're going to subtract 1 from our element that's giving off the beta particle. So here's an example of the beta decay of carbon-14. Carbon has 6 protons, and in this case, it has 8 neutrons. When it undergoes radioactive decay, it's going to keep the same mass, but you can see that it's actually gaining a proton because one of our particles has disintegrated, giving off a proton. One of our neutrons has turned into a proton. Notice that the mass number hasn't changed because protons and neutrons have the same weight. What will be given off is an electron that has no weight, and of course one of our protons will have changed. Again, let's check the conservation of mass and conservation of matter. We had atomic mass units of 14 here. We still have atomic mass units of 14 here because this is 0. For the number of protons, remember one of our neutrons was converted into a proton, which increased our atomic number. So now we have nitrogen. We're going to designate this by saying that we've lost a proton. So it's going to be a negative number. Gamma radiation is a high-energy photon, and that's going to be emitted by a radioactive isotope. Usually we're going to write this as a gamma symbol. It's often emitted with an alpha or beta particle during radioactive decay. This has no mass or charge. It's extremely penetrating and can be very dangerous. It's going to be written as a gamma symbol with 0 and a 0. As there's no charge, there's no weight to this particle. This easily passes through paper, wood, and the human body. The penetration can be stopped, although not completely, by several centimeters of lead. And this is why if you go in to get an x-ray taken, they're going to put a lead apron over the top of you to protect your organs so that only the part that's being x-rayed is exposed to the gamma radiation. Here's an example of gamma and alpha emission from thorium-230. There's thorium. It has 90 protons, and in this case a mass number of 230. When it undergoes radioactive decay, it's going to lose protons. It's also going to lose mass. It will give off a beta particle, or an alpha particle. That when we add this to this, we get back to 90. We add our mass to this, and we're back to 230. And then it's also going to give off a gamma particle.